In this session, we're going to talk about the components found at the circuit's input. The first component we'll look at is the resistor located after the input. This resistor is known as a pull-down resistor, and as you can see, is a resistor with a path to ground. This resistor is utilised to discharge any voltages stored on the input capacitor. It is important to discharge these voltages because if voltages are stored on this capacitor, it can lead to audible pops when the circuit is engaged. As this pedal is a boost pedal, it may be engaged for a momentary section of a performance, for example a lead line or a solo. An audible pop at this moment would be unwanted and have a negative impact on the performance. The value of this resistor also has implications when dealing with calculating the input impedance of the circuit. We'll cover this in the coming weeks. The next component is the capacitor seen here. This capacitor is a dual-purpose capacitor. As we mentioned last session, there is a DC voltage being supplied to the base, allowing the transistor to operate as intended. Well, this capacitor blocks this DC voltage from heading back towards the input and ultimately to your guitar pickups. Capacitors block DC voltage, and this factor is often utilised in circuit designs. This capacitor also forms a high-pass filter. In conjunction with the resistor seen here, they form an RC filter attenuating low frequencies. This is something we'll dive into a bit further. So this is what a passive RC high-pass filter looks like in isolation. This circuit features a capacitor in series with the source alongside a resistor located to ground. To give a brief explanation, capacitors let high frequency content through with more ease than they do low frequency content. Now the amount of low end that they can let through is dependent on the value of the capacitor. As the capacitor's value increases, so does the amount of low end frequencies that are able to pass through. Experimenting and adjusting frequency roll-off points can alter a pedal circuit's frequency content, giving it a signature sound. This is always an area for experimentation when designing a pedal. The roll-off frequency is where the capacitive reactance and the resistance are equal. The frequency roll-off point is measured at -3 dB, and the phase relationship of a high-pass filter is 45 degrees. With this graph, we can see the roll-off point of the RC filter located in the LPB1's input. As you can see, this -3 dB filter roll-off isn't utilised to attenuate a massive amount of low-end frequency content. However, if you were designing your own version of this pedal and you wanted to attenuate low end that is more audible to the human hearing, you could reduce this capacitor's value. This graph shows the frequency roll-off again. However, I have reduced the capacitor's value down to 0.01 microfarads. As you can see, we are letting less low-end content into the circuit. Utilising just one RC filter will result in a one-pole filter. This alludes to the steepness affecting the frequency roll-off. With a one-pole filter, there will be a roll-off at -6 dB an octave or -20 dB per decade. These measurements will be doubled if you utilise the two-pole filter, creating a harsher and more prominent roll-off. You can increase poles by utilising more filter networks. To calculate an RC filter's frequency roll-off, you can use the following equation. 1 divided by 2 pi times the resistance value times the capacitance value. So I'll proceed to plug the resistor value and capacitor value of the LPB1 high-pass filter to demonstrate this equation. This -3 dB frequency roll-off point equates to around 15 Hz. If you're not a fan of using mathematics, there's some good websites that contain good RC filter calculators. I've linked a couple of websites below. So there's a good look at the initial components in this circuit. The next video we'll look at is the resistors involved in supplying the base of the transistor with a voltage and why this is required. See you there.